Hi there. So today's our final look at measures of location and spread before we just do some practice. And we're looking at coding. The reason we need coding is that some data may have very long complex numbers, but it only sort of varies at the end. So if you take a whole load of numbers off, and sometimes if you divide by a number or even multiply, then it can make the numbers just simpler, more quick to work with when you're loading them. It does have a couple of slightly surprising effects though, because if you take a number of everything, then it's going to change what your mean and your different averages are, but it's not going to change how spread out they are. However, if you divide or multiply, it's going to increase how spread out they are. So some kinds of coding affect just the mean, modian and median, and some of them affect your standard deviation as well. So starting off here, we've got temperatures in a nuclear reactor. Boy, it gets hot in there, doesn't it? So starting off, we've got it saying use the coding x minus 300 over 10 to code this data. You could probably do that without me explaining it to you. So x is our temperature, so it's just 332, take 300, which would be 32, wouldn't it? Divide that 32 by 10 would give you 3.2. The next one, 355, take 300, divide that by 10, 55 divided by 10, 5.5. Carrying on, 306, take 300 is 6, divide that by 10 is 0.6, and so on. We get 317 take 300 is 17, divide 17 by 10 is 1.7, and finally we've got the 340 take 300 divided by 10, 40 divided by 10 is 4, isn't it? So there we go, we've got our coded data is 3.2, 5.5, 0.6, 1.7 and 4. I reckon you could pause and give this a go without me telling you, because we've done the mean and standard deviation. So for the mean, hopefully you've just said, right, we're going to be adding up of the coded data, so we're just going to be doing 3.2 plus 5.5 plus 0.6 plus 1.7 plus 4, which is a lot quicker and divide by 5 than putting all of those in. Well, a little bit quicker. So if you're only going to find the mean once, there would be no point in coding, but if you're going to do lots of different things with the data, it's got a reason. Right, so put all of that into the calculator, press equals, and you should get 3. Now, standard deviation, you can get in more than one way. You could use the calculator like I showed you last week. It's only a few things. So, and there are a couple of different ways of doing it. If you look at the top of page 4 of your formula booklet for AS level or A level, then what you get is the standard deviation. One of the definitions is the sum of the mean, sum of the data, sum of the squares of the data divided by how many there are, take the mean squared. So we've already got the mean, so we're going to use this one. So this is going to be 3.2 squared plus 5.5 squared plus 0.6 squared plus 1.7 squared plus 4 squared all over 5. Move that along a bit further, and then take 3 squared for the mean, which we've already got there, and that should give you well, let's whack it in the calculator and find out. .716, so 1.7 2 to 3 significant figures. Now, knowing the mean and standard deviation of the coded data on its own isn't all that useful, because this temperature is not 3.2, is it? The mean is not 3, it's more than that, isn't it? So how much more is it than that? So that's our next question. We've got to convert it back into the mean and back into the standard deviation. So to put the mean back, we have got to reverse the process that we had here. So if I take the mean of the coded information being 3, and the last thing I did was divide it by 10, so if I times it by 10 I get 30, and then if I add the 300 there, I'm going to get 330 degrees, and that makes sense, doesn't it? Looking at the data, that looks about right too. So that's the mean. Now the standard deviation is a little bit different, because the standard deviation is just how spread about it is, and dividing by 10 has made the numbers a lot smaller and it's made them closer together, and so that's going to make a difference. But the taking 300, well, that's kept them the same distance apart from each other, so we ignore the taking 300, and all we need to do is reverse the dividing by 10. So it's going to be 1.72 multiplied by 10 to get rid of that, so that would be 17.2 degrees of standard deviation. Here's some more data. This time you haven't got the actual data, we've got some information which has been partly sorted out for us. So pause the video to see if you can work out what's going on if you like. This here does not mean the standard deviation, by the way, just as a reminder back to last time. This is the standard way of talking about the variance, which is linked to it. So if you look at the top of page 4 in the formula booklet, it tells you that the standard deviation is equal to SXX divided by n, so the variance divided by n and the square root of all of that. So we've got to work out what the mean and standard standard deviation of the maximum gust in knots are. Right, let's sort the mean out first. So the mean, all the data has had 5 taken away from it and then divided by 10. So we need to do the same for our mean. So the mean h there is 2. So we want the mean of G, which is going to be 2 times 10 times 5 times 10, and then add 5. So that's going to give us 25 knots. So that's the easy bit. Then the standard deviation. Well, the first thing we need to do is work out the standard deviation of h. So the standard deviation of h is going to be 43.58 divided by 61 and the square root of that, which sorry about that, which is going to give us 0.845. And what we're going to need to do to that is, because it's been divided by 10 in the first place, is times that by 10, so that we get 8.45 knots as being the typical standard deviation of 1 away from the mean. Practice time. So pause the video and give this a go. Right, so we've got to estimate the mean of the coded values. So this is the data. We've got to code it first of all. So here we've got to code the midpoint, haven't we, before we can estimate the mean of these. So the midpoint there, 21 take 1 is 20 divided by 20 is 1. So I'll have 1 for that one. For here, if I do 23 take 1 is 22, 22 divided by 20 is 1.1. If I do the same process here, 25 take 1 is 24 divided by is 1.2, and then I actually end up getting 1.3 there, and you should have got 1.4 there. Now that we've done that, in order to get the mean and the standard deviation for y, what I would recommend doing is going into the old calculator. So if you've forgotten how to do this, you're going menu, statistics 2, then we're into the table. So on the table, I'm going for the values down here, 1, 1.1, 1.2, 1.3 and 1.4. And then if we come across to list 2, that's where we put our frequencies in, 3, 12, 40, 10 and 5. And then I need to hit calculate and go for 1 var. And on there we've got, the only slightly confusing thing is where it says X, we're actually thinking Y, and then because we've coded it, so our Y bar is 1.20 hours. 2, 3 significant figures. Hence, find an estimate for the mean lifetime of the light bulbs. So, the mean lifetime, what we need to do is we need to reverse this process, don't we? So 1.20 times 20 and then add 1. Well, if you times it by 20, you get back to 24, don't you? Add 1 is 25 hours, which means all we've got left to do is the standard deviation of the lifetimes of the bulbs. So what I would do first, if we're looking on here, I've got the standard deviation of y just there, so standard deviation of y is going to equal 0.08778, put a little bit more in there. And then it's only how far apart is only affected by the dividing by 20, isn't it? Not the take 1. So I just need to multiply that by 20 and I get 1.76 hours. Last question then. Pause this one and give it a go. Right, so we're back with the large data set. Not that it really matters, it's just some information, isn't it? And we want to know the mean and standard deviation of the daily mean prediction. Now they've given us the mean of the coded stuff already. So the mean of P, which will be the daily mean, the actual one, will be just reversing this process. So it's been divided by 2 and then had 500 taken away. So we're going to need to add 500 first, and then whatever that is, times it by 2, which gives us 1020.3 to 3 significant figures. That's 1020 HPA. Something Pascals, can't remember what. Anyway, moving on. First of all, we've got the variance, so we need to find the standard deviation from that before we can code back, because this is like halfway through to find it. So the variance is what we've got. So if we find the standard deviation of this by dividing the variance by 30 and rooting it, we get root 247 over 5. And then if we want to get the standard deviation of the actual data, we need to get rid of not the fact that it's had 500 taken away from it, because that has not made any difference to how spread out the data is. The only thing that's done that is they've all been closed together by a factor of 2 because they've been halved. So we need to reverse that. So we need to do root 247 over 5 times 2. Press S to D on the calculator, round it to 3 significant figures, you should have 6.29 HPA. And that's it for this week, folks. Happy coding. Next week we will do some practice of all the stuff from this whole topic of measures of location and spread, and then we'll be ready to move on.